5.1 Systems of Linear Equations. Example 1. Determine if the ordered pair 0, -1 is a solution to the system. So that's an example of a system, y equals 3x minus 1 and y equals 2x plus 1. A system is basically more than one equation, and this is a system of linear equations because both of those equations are both linear equations. They are in the form y equals mx plus b. So just for bookkeeping, I'm going to label that first equation, y equals 3x minus 1, I'm going to label it number 1, and I'll label the second equation, y equals 2x plus 1, I'll label that 2. So we want to determine if the ordered pair 0, -1 is a solution to that system. So here's how this works. If an ordered pair is to be a solution to a system, then it must make all equations, 1 and 2, true. So if it just makes one of the equations true, then that ordered pair is not a solution to the system. If it makes none of the equations true, well then obviously it's not a solution to the entire system. So let's test the point. We're going to let x equal 0 and y equal -1. We'll first test the first equation, y equals 3x minus 1. So I'm going to replace y with the -1 and 3 with the 0. And then I want to know, is this a true or false statement? Simplifying, I see that that is a true statement. So I know that the point 0, -1 is a solution to the first equation, but that's not enough to say that it's a solution to the entire system. I also need to ensure that the point or ordered pair 0, 1 is also a solution to the second equation as well. So that equation is y equals 2x plus 1. So again, if I let y equal -1 and x equals 0 and simplify, I'm looking to see if I get a true or false statement. And I get -1 equals 1. That is a false statement. So a solution to a system is an ordered pair that will make all equations in the system true. That is not the case here. Therefore, the ordered pair 0, -1 is not a solution to the system. All right, so when we are talking about systems of linear equations, there are going to be 3 scenarios that we're going to run up against, and these are the 3 different scenarios, and I'm doing this from a graphic or visual perspective or point of view. So the first scenario is, let's say you have a line, I'll say that that's L1, and then another line, L2. So this is a system of linear equations because it has two lines. This system has one solution right here. Whatever that ordered pair is, that is the solution. It kind of looks like it's -1 up 2 or up 3 or something like that, but that is the solution. So this has one solution. Solutions to systems occur wherever all of the lines in the system intersect. So these lines intersect once, so it will have one solution. Here's another scenario. Here's line 1, and here's line 2. These lines are parallel lines. This means that they have the same slope. They go forever in each direction and they never intersect. So they have the same slope. So the slope of the first one is the same as the slope of the second one. Because they never intersect, they can never have a solution. So this is one scenario, another scenario for systems of linear equations where we would have no solutions. And an algebraic example of a system that would fall in this category is this: y equals 2x plus 1 and y equals 2x minus 3. We can see that they have the same slope, which means they're parallel, but they have different y-intercepts, so they're not the same line. So the fact that they have the same slopes means that they're parallel and they will never intersect, thus no solution. The third scenario is this. Here's the first line, line 1, and then watch this. Here's the second line. They're the same lines. So if they're the same line, then they intersect at an infinite number of points along the line. So they have an infinite number of solutions. In this scenario, the slopes are the same and the y-intercepts are the same. They're the same line. So an example, algebraically, of a system that would fall into this category is this. Y equals 2x minus 1 and 2y equals 4. I'm sorry, I wanted that to be 1. So y equals 2x plus 1 and then 2y equals 4x plus 2. Now at first glance, it appears that they have different slopes and different y-intercepts, except that if you simplified the second equation, 2y equals 4x plus 2, for example, if you divided the left by 2 and divided the right by 2, you would see that it would be the same equation as the first one, y equals 2x plus 1. Thus, they are the same line, they have the same slope, same y-intercepts, therefore they would have an infinite number of solutions. Example 2. Find the solution, which is another way of saying solve the system, y equals 3x minus 1, y equals 2x plus 1, using the graphing method. So before this, we were testing to see if an ordered pair was a solution. We were also looking to see how many solutions there were. So right now, we're going to begin finding and solving for the solution. There's 3 methods that we can use to solve or find the solution of a system of linear equations. The first method is called the graphing method. So the graphing method requires that we graph each equation in the system. So for example, if I take the first equation, y equals 3x minus 1, it has a slope of 3, or 3 over 1. So I'm going to rise 3, run 1, and it has a y-intercept of -1. So to graph that, I start with the y-intercept. Let me get some points on here. All right, so I start with the y-intercept over 0, down 1. And now I'm going to rise 3, run 1. Rise 3, run 1. All right, so I can go do more points if I need to, but for right now, I'm going to jump to equation 2, which is y equals 2x plus 1. So this has a slope of 2, which means I rise 2 and run 1, but before that I need a point, so I'll use the y-intercept, which is 0, 1. So I go, actually let me first graph this line, the first line. That is L1. So now the second line, 2x plus 1, I start with the y-intercept of over 0, up 1, and I'm going to rise 2, run 1, rise 2, run 1, rise 2, run 1, and that looks something like that. So that is L2 and that was L1. So it looks like the intersection is happening right here. So that is over 2, up 1, 2, 3, 4, 5. So that is the point over 2, up 5. So solutions occur where the lines intersect. Therefore, the solution is the point 2, 5. I want to point out that when we were in example number 1, we were testing to see if the point 0, -1 was a solution to the system. And we said it was not. And you can see that the point 0, -1 is a solution to the first one, L1, but it is not on the second line, which means that it cannot be a solution to the entire system. Example 3, solve the given system, which means find, and we're going to use the substitution method for this one. So I mentioned that there was 3 ways to solve a system. The first method was the graphing method, which we used in example 2. The graphing method is really only useful if the intersection of those 2 lines falls exactly on grid lines, which it did in example 2. In example 2, the intersection of those 2 lines that we graphed was 2, 5, right 2, up 5. But what if it didn't fall exactly on a grid mark? Like what if it was in between, like maybe right 2.131 and up 5.3 repeating? That would kind of make things a little bit more difficult. So we would need a method that is more exact and precise. There are 2 methods that are more exact and precise than the graphing method. They are both algebraic methods. The first of those methods is the substitution method. The second of those 2 methods is called the addition or elimination method, which we'll get to in a moment. But for right now, let's work on the substitution method. So for example, if we have a system of linear equations, I have 2 equations, 1 and 2, which I label for bookkeeping purposes. The first step in the substitution method is you pick an equation, 1 or 2, it doesn't matter which one, and then you solve that equation for either x or y. It doesn't matter which variable. So there's 4 different ways you could start this. You could take equation 1 and solve for x, or you could take equation 1 and solve for y. Or you could take equation 2 and solve for x, or you could take equation 2 and solve for y. It doesn't matter. However, there is one method that is the easiest method. It will make things much more easy for you, and that is this. You pick an equation and solve for a variable that has a coefficient of 1 or -1. So that means in this scenario, we should take equation 2 and solve it for x, because the coefficient of x is -1. The other coefficients in this system are 2, 5, and 6. We want to solve for the variable that has a coefficient of 1 or -1. So first step is to pick an equation, which I did, equation 2, and solve it for a variable x or y. I'm going to solve for x. And I get x equals 6y minus 8. So the second step in the substitution method is you take what you solve for and you plug it in to the other equation, keyword other. If I started with equation 2, then the other equation would be equation 1. And I plug it in wherever there is that variable, which in this scenario is an x. So if I let x equal 6y minus 8, I get an equation with just y's in it, which is nice because I can solve that for y, which is what I'm going to do next. So I'm going to distribute that too. Combine like terms. Add 16 to both sides. Divide both sides by 17, and I get my first variable, y equals 1. Now when we're solving a system, we're looking for an x and a y, or the ordered pair. I have the y equals 1. So here's how we find the other variable. We pick equation 1 or 2, it doesn't matter, and we substitute y equals 1. So I'm going to pick the equation that I think is most easiest to plug in a 1 for y and solve for x. And to me, that would be equation 2. So I know that in this scenario, y is 1, so I'm going to let y equal 1. and now I can solve for x. And I get x equals -2. So we can write our answers like that, or if you prefer to write our answer as an ordered pair, it would look like that. So if we were to use the graphing method and graph these two lines, we could solve each of them for y equals mx plus b, graph them, we would find that their point of intersection would be the point -2 up 1. Example 3, part B. Solve the given system using the substitution method. All right, so we've got two equations, 1 and 2, and we want to choose any one of those equations and solve for either x or y. It doesn't matter. However, it is easiest for us if we select the variable that has a coefficient of 1 or -1. So that means we're going to choose equation 1 and solve for x. I get x equals 3y. So now I want to plug that into the other equation. So if I started with equation 1, then the other equation would be equation 2. And where I plug that in is in its corresponding variable, which is x. So I'm going to replace x with 3y. That gives me an equation with just y. I can solve for y. So that's a 2y. It looks like a 24, but that's 2y. So then I have 17y equals 0. Dividing both sides by 17, I get y equals 0. So that's my first variable. To get the the last variable, x, I can choose either equation 1 or 2. It doesn't matter. To me, equation 1 looks more friendly. And I'm going to let y equal 0. And x is also 0. So we can write our answer like that, or we can write our answer as an ordered pair. Thus, if we were to graph that system, solve for y equals mx plus b, and graph those two lines, we would find that they would intersect at the origin. Example 3, part C, solve this given system using the substitution method. So I've got two equations, and I can choose any equation, 1 or 2, and solve for either x or y. Well, that's actually already done. We have an equation that's already solved for y. In fact, we have two of them. So let's say I choose equation 2 and I solve for y, which is already done. And then I plug that into the other equation, 1, where there is that corresponding variable. That gives me this. So I just plugged in 1/5 x plus 4 into that y, and that should equal this. So essentially, we just took the two equations and set them equal to one another, which is actually a legit math move, because if two things both equal the same thing, y, then it is legit to set them equal to each other because they must be the same thing. They both equal y. So I now have an equation with just x in them and x in it, and I want to solve for x. So I notice that the LCD of 5 and 7 is 35. So I'm going to place, I want to multiply every term by 35, or I want to put a 35 in every numerator. So it would look like this. 4 times 35 is 140. Then I can do a little simplifying. 35 divided by 5 is 7. Divided by 7 is 5. And then 35 divided by 7 is 5. So I now have 7x plus 140. Cleaning that up a little bit. All right, solving for x, I'm going to subtract 7x from both sides, and then I'll subtract 10 from both sides. So that gives me and x equals 10. So that's my first variable, x equals 10. To solve for y, I want to plug a 10 in for x into equation 1 or 2. It doesn't matter which one. Now if I'm going to plug a 10 in for x into either one of these equations, wouldn't I rather plug it into equation 2 because of the 1/5, the denominator of 5? 10 can be divided by 5, but 10 cannot be divided by 7. Therefore, I think it's much easier to choose equation number 2. And if you didn't understand that, then you'll see it happen right here. You'll see what I was talking about. If I let x equal 10, then you'll notice that 10 can get divided by 5 to give me a 2. That would not have happened if I chose 4 over 7. If I plugged a 10 in here, 10 would not divide evenly by 7. So that was equation 2 was a better choice. So I can write the answer like that, or as an ordered pair, 10, 6. Either one would be fine. So if I were to graph those two equations, I would find that they would intersect at the point right 10 up 6. All right, we are solving systems of linear equations, and we've previously done two methods, graphing and substitution. The graphing method is good for if the intersection of the lines falls exactly on a grid mark. If that's not the case, then we need a more exact and precise method. That's an algebraic method, and the substitution method is an example of that. Another precise algebraic method of solving systems of linear equations is called the addition or elimination method. Some people call it the addition method, some people call it the elimination method. Both words are equally descriptive of what happens when we do these problems. So here's how the addition and elimination method work. If we add down, then x plus x is 2x, y minus y is 0y's. 1 plus 3 is 4. So it's called the addition method because we add. And when we add, a variable eliminates. In this example, the y variable eliminated, and that's why some people call it the elimination method. Either way, you can see that we've already got our first variable. So that was actually a really quick way of getting to our first variable. So now to find the other variable, y, we can pick either equation, 1 or 2, it doesn't matter, so choose the one that you think is easiest. I think most people would probably pick the first one only because it doesn't have a negative in it. I don't know that it makes it easier or not easier, but most people don't like negatives. So if I let x equal 2, then that gives me 2 plus y equals 1. Solving for y, I get -1. So I can write my answer like that, or I can write it as an ordered pair. Either way is fine. Example 4, solve the given system using the addition or elimination method. All right, so the first step in this method is to add down, which is actually, it works for x and minus 4x, but that's problematic for the other terms because 2 and 3y are not like terms, and 2y and 25 are not like terms. So whenever you use the addition and elimination method, before you even start, you have to make sure that your x's are lined up vertically, your y's are lined up vertically, your equal signs are lined up vertically, and your constants are lined up vertically. So the first thing I'm going to do is rewrite the system. My x's will go first, then my y's, then the equal sign, and then the constant. So there's my new equation number 1. It's the same equation, I just rewrote it. I'm going to do the same thing for number 2. All right, so that is my new system of linear equations. I just rewrote it. So now my variables are lined up. So now I can add down and I get, so x minus 4x is negative 3x. 2y plus 3y is 5y, and 25 plus 2, it gives me 27. Now, we've just run into another issue with this problem, and that is nothing eliminated. So that didn't work out. So what we're going to do is multiply the first equation by a positive 4, because when I do that, this is what I would get. So now I'm going to have yet another system of linear equations that I'm rewriting. So that if I multiply the first equation by 4, I get that. That is my new number 1. Because, and that's legit, whatever I do to one side, if I do it to the other side, that's okay. Number 2 will remain the same. So that is my new system. It's the same system, I've just rewritten it. So now, when I add down, the x terms will get eliminated. Oops, there's my y. So we can see that the x gets eliminated and y equals 3. So now I need to pick equation 1 or 2, it doesn't matter. And I can pick equation 1 or 2 in any of those 3 systems. However, it is a good practice to get in the habit of choosing one of the original equations that we were given in the original problem. So with that being said, I want to solve for y, and number 1 is already solve for y, or I'm sorry, I want to solve for x, and number 1 has an x equal, so I think number 1 is really a good one to use here. So if I use equation 1, and I let y equal 3, I get x equals negative 4. So I can write it like that, or I can write it as an ordered pair, negative 4, 3. Either way is fine. Example 4, part C. Solve the given system using the addition or elimination method. All right, so I notice that first off, my x's are lined up vertically, my y's are lined up vertically, my equal signs are lined up vertically, and my constants are lined up vertically. So that's good. I also do some quick calculations in my head, and I see that if I add down, none of the variables are going to eliminate. So that means I need to multiply one of these equations by something. And if I multiply one equation by something, I do not have to multiply the other equation by it. Maybe I multiply 1 by something, maybe I multiply equation 2 by something, or maybe I multiply both equations 1 and 2 by something. There is no cookie cutter way of doing this, and in fact, some of you will do it differently than others, and that's fine. One way of doing this is I could multiply equation 1 by a 2, in which case I would get a 6x, and then I could multiply equation 2 by negative 1, which would give me a negative 6x, so when I added down, my x's would eliminate. Or I could combine both of those into one and just multiply the first equation by a negative 2. If I multiplied the first equation by negative 2, that would give me a negative 6x, which would eliminate when I added it down with the 6x in equation number 2. But that's not the only way. I could eliminate the y's. So the y's have a positive and a negative, which is actually good, because if we want something to eliminate and add to 0, something's got to be positive and something's got to be negative. So if that's the case, if I wanted to eliminate the y's, maybe I multiply the first equation by 5 and the second equation by 7. So if I multiply the first equation by 5, that would give me negative 35y. If I multiply the second equation by 7, that would give me positive 35y, and adding down, those would eliminate to 0. I think that in here, and there may be more ways that you see, either of the ways is fine. I personally think that multiplying this first equation by a negative 2 is the most efficient method, so I'm going to do that. All right, so I'm going to multiply that first equation by a negative 2. And I have to remember to multiply all the terms by negative 2, even the constant. Now the second equation is going to remain the same. So there's my new system, and now I'm going to add down. So you can see that my x's eliminate. 7 minus 26 gives me negative 19. So I have 19y equals negative 19, y equals negative 1. There's my first variable. That's the part that takes the most work, getting to the first variable. Once you have your first variable, it's always the same way to get the second variable. We can choose either equation 1 or 2, it doesn't matter. I recommend that you get in the habit of selecting one of the equations in the original problem that we were given. So I don't know which one is going to be the easiest, so I'll choose number 2 since it doesn't have a negative in it. So if I let y equal negative 1, I get that. Solving for x, I find that x is 2. So we can write our answer like that, or we can write it as an ordered pair, 2, negative 1. Either way is fine.